So we're talking about convection now, and convection is another form of heat transfer. This type of heat transfer occurs in gases or liquids. Collectively, we would call those fluids. Now, when we talked about conduction, we were talking about the transfer of energy or the transfer of heat through particles, particle collisions. We are still talking about particles, but this time, like in the case of my bonfire down here, we're talking about gas particles. If you put your hand above a flame, it feels very hot. If you put your hand to the side of the flame, it doesn't feel as hot. It can still feel warm because of radiation, but not as hot as it feels when you put it at the top. So why? Well, you have to first of all remember that the gas is a material. You can think of gas as a material, therefore it is made of particles. These particles are in random motion. Okay, so they're all moving around, colliding into each other. If a particle gets close to the flame, it gains heat. So I've tried to use blue to represent the coldest particles, green, cool but slightly warmer particles, and red for hotter particles. So these particles move over here and they get a bit warmer. As they get warmer, remember, they move around more. Okay? So heat to a particle is just like energy for a small child. If you give a small child some candy or some sweets, they eat that, they're going to be full of energy and they'll move around more. And they'll move and move and move. Very energetic. Particles are the same. You give them heat, you give them some heat, and that's their energy. And they will move around more. Because they move around more, what do? They expand. Each one crashes into another one, taking up more space overall. Just like a crowded bus full of children. One of those children you give lots of sweets to, lots of sugar, lots of candy. They've got too much energy. They can't stand still. They're moving around. They're crashing into their friends or other people on that bus, and they take up more space. If a particle takes up more space, then we say it is less dense. Things that are less dense, like we looked at in an earlier video when we looked at bubbles, things that are less dense, like gases inside liquids, they float or they rise up. That's exactly what happens with our particles here. These particles gain some energy, they move around more, they take up more space. I've tried to spread out my particle pictures a bit more. As they do so, they become less dense. That means they're pushed up or they rise up, they float up. If those particles move up, they can collide with other objects, people, walls, ceilings, anything, whatever's around, just other air particles that are cooler. This means that these hot particles start to lose their energy again. As they do, they slow down. Less kinetic energy means less moving energy. Less movement means less space that they take up. They then start to fall down. If you put a heavy dense object, like some metal or a brick, and drop it into water, bloop, it will splash, it will sink. And that's what happens with these air particles. They become closer and closer together as they get cooler, and so they sink down. But there are more particles over here, and as they move up, they get hotter and hotter. The particles move away, it creates some more space for these other particles to move into. They essentially get sucked in. It's a sort of pressure gap that they leave behind. And so they're brought in, they get hotter, and they turn into these red particles again. So if we were to follow the path of one particle, I haven't got a different colour particle, let's just go with this green one. One particle, here it is, cold, just moving around a little bit, more so than any liquid or solid because it's a gas, but still not really going anywhere. But it's being pushed along by all these other particles. There's space over here creating a vacuum, sucking it in. And it goes, gets closer to the fire, gets some heat. Hello, it starts to move around a bit more, getting a bit more excited. As it goes up here, it's got more energy. It's moving around more, taking up yet more space. And it goes higher, further away from the fire. As it gets further away from this heat source, we now have an object with heat, with energy. The universe is a lazy thing. The universe is lazy. It wants to get rid of this energy. This particle is part of the universe. It wants to get rid of that energy, too much energy. It does that by colliding into other slower moving particles. That slows it down. It loses some of its kinetic energy. It becomes less dense, and so it starts to sink and fall down. That process can continue and continue in a cyclic-like style. And so we actually, when we talk about convections, we quite often talk about a convection current. Our colder, cooler air is brought in. It starts to heat up as it gets closer to the flame. And then it gets much hotter. And then it begins to cool. Until we're back to our colder air. And so that whole thing is called a convection current. It's this cyclic process, a convection current. So, to summarize, gas particles gain kinetic energy. That movement makes them less dense. The movement from all that kinetic energy makes them less dense. Less dense things rise up. Cooler particles, or once these hot particles give away their energy now, they cool down, and the cooler particles sink. They replace those hot particles that are being drawn up, and so we get this convection current, this cycle on both sides of the flame. Think about different situations where you know that convection currents occur. I'm going to show you one little demonstration that I've put together as well. Okay, so I have here a small box. It's got these two chimneys there. So this is a convection chamber. I made it myself, that's why it looks so terrible. I've put some aluminium foil purely just to reflect heat. Because what I don't want to happen is I don't want this box to set on fire, obviously. Inside, I don't know if you can see that, but I've put some candles. They've all just fallen over now because I've tilted the box. But I'm going to try and stand those up again. I'm going to light those candles. Once they're lit, we should be able to see some convection currents. Well, we won't be able to see those convection currents, but there should be some heat rising up, or some hot particles rising up from that fire. So I can then close it, and we can see if there is a difference between the output, if you like, of these two chimneys. So let's have a little look. So first of all, I want to light the candles inside. So now we've got a fire going. Hopefully it's not too strong. Okay, so I'm going to close the lid. And now we can't see what's going on inside, so you'll have to just listen to what I say for a minute. Okay, so we've got two chimneys here. You can probably see there's a bit of a glow coming out of this one. This feels very hot. If I put my hand here, I can feel heat coming out of this chimney. If I put my hand here though, I don't feel much heat at all. In fact, I can feel cool air. It's almost like the air is being sucked in. But here I can feel hot air coming out. Okay, so let's test that. That's 17.2. Okay, so this is staying cool air. I mean, it's not going to be any colder. This thing can't produce cold. There's no such thing as cold energy, but it's just the air in the room. I can feel it being sucked down. So that's our temperature. If I put the temperature probe here, above this chimney, we can see it starting to rise up. Okay, 18 degrees, 19, 20, okay, it's getting hotter and hotter. So there must be hotter coming out of here, but the cooler room temperature air going down here. And so if there's cooler going down here and hotter coming up here, then what we have is a convection current, like what I just showed you on the board. And finally, if I can create some smoke, hope this doesn't set the whole school alarm off. Or simply a load of fire. Okay, if I put that smoke here by this chimney, we might get enough. Oh, probably my fire's gone out. Hold on. Can we see it getting sucked in? Nope. Okay, some of the smoke should start to get sucked in. There we go. We've got some of the smoke being sucked down this chimney now. Okay. Sorry, not a very good example, but at least we saw it a little bit. Yeah, might be a better example. Sorry, not having a lot of success here, just a lot of smoke. So now you can see the smoke being sucked down here. See that? And that's because of the convection current. So we've got smoke being sucked down here, and now you can just start to see it coming out the top as well. So that's our convection current. Bit of this little bit of tissue paper, it's being pushed up here. It's being sucked down here. Only slightly being sucked down as gravity, of course, but here you can quite clearly see it's getting lifted up.